Okay, welcome to the sanitised version, I guess, of our recordings. It's very important that we have attendance at the lecture, I think, but apart from that, this is the catch-up video, so if you weren't there for whatever reason, then you can peruse this. Alright, so I made a big emphasis about the whole idea of making sure that you had some strategic intent. It's very important that you have strategies, because if you don't have strategies, you're not going to pass this subject and you're not going to pass university level maths. So you'll be hearing me talk about this quite a bit. So you need to develop your strategic ideas, and then these strategic ideas will be things that you own as a university student moving forward in your mathematics study. It's important, of course, that when we get to this level of study that we don't feel as though we're completely overtaken or overwhelmed by what's happening in a maths subject at university. So we need to take on board some of the ideas that are presented as they're proven. They're very much proven in terms of how we go about getting student success in mathematics at this level. Alright, so one of the big ideas is the big idea of recognition. And the analogy that I used for recognition was that there's some new information in terms of language. Forms is something that I'll emphasise all the time, and that the forms are often just substitutable. They're two forms of the same thing. So that's a very important concept. I've talked about the idea of the recognition of a little loved one, and as you embrace your studies, we can imagine that there's a whole bunch of people all over in a particular location, and we are looking for one particular person. And all of these, it's intended, of course, that these are us looking out and trying to see who it is that we can find, our lost little loved one. And our lost little loved one can only be identified, there you go, that one, by the means of recognition. Okay, so if you haven't got your recognition, there's no way in the world that you're going to be able to pull that particular little lost loved one out of the crowd and say, I've got you. Maths lectures are much like that. We have little nuggets of ideas and concepts that we're teaching, and often you'll pull up a blank, and if you have a blank, it's like, no, what do I do? What do I do? Well, the main tool that you'll have as a maths student is recognition. All right, before we get to the rest of the beginning of the lecture, we'll go over a couple of very important things. And I'll start with the less important of the two, and that is for you to develop a meta-understanding. Now, basically, a meta-understanding means that you know the difference between what's analysis, what's computations. And that's a big deal, because analysis questions are the ones that make your heart flutter and your adrenaline pump. They're the ones that make you nervous. Analysis questions are the culprits of making you not like mathematics. So the mathematicians and statisticians love analysis because everything about maths is built on analysis. And so what we get is an inkling. We only get a sprinkling of introduction to analysis as we go through school. And likewise, when we come into our first couple of computations or applied mathematics type questions. So analysis is still there, underpinning the theory of how these things are done, but the way that we touch on it varies very much from subject to subject. So an example of a university subject is usually universities call these subjects real analysis. And you can go on and do that as an elective if you want to. There's complex analysis. There's many, many more things that'll verse you and put you in the right realm for the study of analysis. For our part, we want to conquer mostly computations and understand the tools and the techniques that are needed for computations. So I will prompt you to notice the difference between the two particular areas to help you develop a response to questions as you go along. Sometimes you'll be able to just stop and say, no, that's analysis. I've done as much as I need to do here. No further inquiry there is going to help me solve the problem. So I'll get on and solve the problem. All right. So these 6 things are the answer. As a student in foundation mathematics, you need to be able to do these 6 things, and you need to be able to do them really, really well. And that means that sometimes I'm often called the long way teacher. That is, I don't miss lines of working. Sometimes you get a line like this and you kind of like, how did we get from that line to that line? Or how did we get from that line to that line? Well, I'll often put in that, and that makes for a long-windedness sometimes. And some students are a bit annoyed by that. Oh, we've got to go through all that. I could have done that in 2 lines. Okay, fair enough, but I've got to teach 500 students, not just you. So if you're someone who's really good with the skipping of the ideas and filling in, that's great. But if you're not, that's okay too, because I'm the long way teacher. That means we're going to bow down to some ideas of earlier schooling. So I'll be talking a little bit about Year 6 and how we use information in Year 7 and 8, and particularly Stage 5. The bulk of these ideas are Stage 5 ideas, okay, which is Year 9 and 10 at school. And then we've got a couple of advanced ideas. But fortunately, we don't have to do them in the same way that we do them in the HSC. So that's a good thing. But this is your job. You cannot go through this semester and not learn these 6 things. Okay, your job is to become masters of these 6 things. I can hear you talk about calculus. Well, we'll get to that. You'll hear me say on many occasions, calculus is not the problem. All right, at some point I think we need to start to develop all of these ideas into a learning journal. It's not formal for the subject, but it may be in the future. For the time being, it's just about notes and ideas and sketching out things that make you understand your mathematics and help you when you go to peruse or study. And these kinds of things are very important. So in fact, I want you to develop a cheat sheet that you can take into your assessments. Yes, you heard me correctly. Something that you can look back on and understand. A lot of students write stuff out, then they go back over it and they can't even understand their own writing. So we'll need to develop that. And the final idea is really around assessment. We need to come to terms with assessment. Assessment is often given the bogeyman status as you come out of school. It's all about pressure and can I do it or can't I? No, it's none of those things. It's about us expressing what we know. When I work, when I do this stuff here with you guys, I hope that what I do you gain a benefit. So that's my work. That's my assessment. We're all being judged. I'm not judging you. Of course, I've already explained that to you in the lecture. But I'm really happy for you to take on board the things that I'm saying, good and bad, and push back to me and say, hey, Jason, that could change a little bit, or that could be fixed up a little bit. I'm happy to take that feedback because that's you assessing me, and I'm okay with that. So the outputs that I have, it makes me happy when I see students do really well. So I've taken a lot of students from no maths to getting ready for Mathematics 1 and succeeding, not just doing well, but really achieving high results in Mathematics 1. And I've done that for a very long time here at UTS now. I've been here over a decade, so that's been happening for quite a long time. So as good as any place to learn about, demonstrating your outputs is a university. Demonstrating your outputs is a great thing to do. It's good training for the workplace. And, of course, a math subject is a good place for that. All right, so perhaps you can start with self-assessment in the form of homework. Now, I've talked a little bit about homework and the importance of doing that. There's a lot of questions in the Pearson homework, but it's only worth 10%. So I've deliberately made a bit of oh, wow, I wish homework was worth more and then we could just pass the subject on homework. There are subjects like that in the university, but foundation isn't one of them. So we need to understand that we can develop our skills doing the homework and doing other studies and getting ourselves ready for the basic skills tests that we'll have to do. Because those formal assessments are just measures of outputs, aren't they? And what you're able to tell me. Tell me what you know and what you've learned, and that's really all an assessment is. Okay, you've got a curriculum being studied, and you just need to help me do that. All right, so let's have a look at some ideas for development. And so basically what we've got is, adding fractions. Really? You're going to talk about adding fractions? Year 6 stuff? Come on, man. Well, actually, that's it, isn't it? When we multiply fractions, we can get a fairly good idea of what's happening with our multiplying of fractions. We just multiply across the top and multiply across the bottom. So we get 1 times 1 is 1, that's 6 7 is 42. So often what we take for granted is that the things that we learn, we forget about the backgrounding and what it actually means to develop a skill set, because we just pick up a basic idea like this and we just deal with this in the moment. And then if there's something else coming along like adding fractions, then we often forget ourselves. So the development of a vocabulary is going to be very important. It's a bit like asking the question, what's multiplication? What's multiplication? So if I have groups with 3 in them, what is multiplication? It's just adding groups. It's just counting in groups. So if you can count, you can do mathematics. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We've done it like that as well. So I've never met a student who hasn't been able to learn their times tables, no matter how young they are, just by following that through. And sometimes it's labour. But if you don't know your times table, that's really what you're aiming to achieve, because you're going to encounter having multiplication. All right, so what about if we get a version of this that goes like that? I don't know what to do with that. Oh, yes, you do. You just take the second one and you flip it over. Okay, so you've got 7 1s are 7, 6 1s are 6. So it's 1 and a 6 if you want to go back that far. That's fine. All right, so we're able to do divisions. Well, what about if we get a bit tricky and put some algebra in? Because we like the gymnastics in algebra. Oh, well, that's all right. Just multiply across the top and you get a 1. A times D is just AD sitting next to it. So you'll get used to algebra as we go on, because I'll afford plenty of time for that. All right, but it says adding fractions. So what about adding fractions? So we can take this old idea of adding fractions and say, all right, adding fractions. That's like having half a pizza added to another. That's a very year 6 idea. I'm not sure that helps us at university. I'm not even sure it helps us going into stage 5. But it's a concept, an idea, but it doesn't help us do the next bit. So let's have a think about the next bit. What if we were to take something a bit more unfamiliar, and we could do that one in our heads. We could say, oh, 1/3 and 1/3 is 2/3. But what's the mechanism? Well, the mechanism is that we take a look at the sign and we ask ourselves, is it a times, divide, plus or minus? And we decide it's a plus or minus. And based on that decision, we then ask ourselves, are the denominators the same? So we write denons equal. And if the denominators are equal, then we can just go ahead and do our task. So in this case here, we've got the same family. So we can do 1 plus 1 and we get 2/3. So that's the output there. That's that output there. But what about if the denominators are not the same? We have to create the same family. Okay? Now this all seems very rudimentary. Some of you will be annoyed with me for taking the time to do this. But as I said, I'm teaching many, many students, not just you. So 1/4 plus 1/3 is an example of a fraction that we will add. And the whole pie idea kind of falls away now. You can draw the pizzas and the pies and slice them up into particular parts, but it doesn't help. So this is really a big moment in foundation maths. This will lead you forward if you're able to conquer this at some point. So what we want to understand is that when we're adding fractions, we don't want to change the quantity. Now, you can make a little note, okay? And that's almost like your journal. We don't want to change the quantity. So we don't want to make 1/4 something else. We don't want to make 1/3 something else. We want to make it the same. They have to be an equivalent. And the adding fractions mechanism works this way. So what we do is we decide step 1, okay, they're not the same, so we're going to go to step 2. Okay, and the way that we would do step 2 is that we would multiply the denominators and we would create a new scaffolding based on the product of those denominators. So 4 times 3 is 12. and 4 times 3 is 12. And what we can't just go ahead and put ones up now because we've changed things, but we've made the same family. So the denominators are equal now. Okay? The result of doing this is that we've made the denominators equal. Okay? So our dens are equal, which is what we wanted. So how do we not change the quantity? Well, what do we multiply the 4 by to get 12? Well, we multiply it by 3. So what we're going to do is we're going to multiply this by 1. And I hear you groans, oh, come on. Are you serious? What do you notice about this? The number in this column is not being changed. There's a concept. So the 1 times table doesn't change the term. It's an equivalent. Now 1 is my favourite number because we know that whenever we multiply by 1, as in the 1 times table, we don't change the quantity. So that's a mathematical. So we can use 1. Now, the thing that we know has many different forms. Okay, it has many different forms. So we can invoke 1 to help us with this equivalence problem. So we multiplied it by 3. So what we do on the bottom, we do on the top. So we're multiplying 1/4 by 1 in disguise. 1 in disguise. So we're not changing the quarter at all. 3 4s are 12. 3 1s are 3. 3 12ths is a quarter. Now, some of you will say, I recognise that from year 9. Get on with it. But some of you have not had this training in this way. And so this is now a very important moment. What did we do to the 3 to make it a 12 over here? We multiplied it by 4. There it is on the bottom. But we want to multiply the quantity by 1 because we know from the 1 times experience that we won't change it. So our 1 in disguise is 4 over 4. We're multiplying 1/3 by 1. 1/3 times 1, 1/3 times 1 is equal to 1/3. We're not changing it. So 3 4s are 12, tick, and 4 1s are 4. So now we've inserted this intermediate step. It's like in here, isn't it? We've put something in between because we've generated the same family. Now we can go to our common denominator and 3 plus 4. So 3 and 4 is 7. Okay, so these mechanisms, while being played out at some length here, while being drawn out some length here, are absolutely vital to your success at university level mathematics. Adding fractions is going to raise its head in a lot of different ways. Okay. Now, what about if we make it a bit more interesting? And I think during the lecture I made a point of saying Aaron times 1. Sorry if I got the spelling wrong. Is Aaron. Okay. I think we had an Isa times 1 is still an Isa. Okay. Jason times 1 is still Jason. Okay. Box times 1 is still box. Car times 1 is still car. It doesn't change the quantity. The concept of 1. An integral menagerie that we're not familiar with yet, multiplied by 1, is still the integral menagerie. We'll learn about that this semester. But look at what we're doing. We're using the 1 times concept to make that apply. Now, does it look different? Sure does. If you were to say to me 1/4 plus 1/3 is 7/12, really? You're a lot smarter than me if you could jump like that. So the rest of us, we need to be human and take our steps. Okay? Sometimes the unfamiliar plays out. What we can do here is we can take confidence in our procedures. We can take confidence in our procedures. Okay? So if we do that all the way through, we'll become really good. We'll be really good at generating solutions to problems. So let's have a look at another example. And let's change it a little bit. So we've got, okay. First step, I'm not going to mark them all up. I'll let you mark them up yourself. 1 over A, 1 over C. Okay, is that a plus or minus? Tick. Yes, it is. Are the denominators the same? No. The dens aren't the same, so we have to make a new family. We do that by multiplication. So we're going to multiply. We're going to make a new family. There you go. There's our minus. That's that minus. Our new family is the product A, C. And they just sit next to each other, don't they? A times C is AC. A times C is AC. Okay? But we're not going to change the quantity. We can't change 1 over A into some other quantity. It has to maintain. So what did we multiply the C by? A by C. Oh, look. Wow. It's a completely new one. So provided we get the concept that we're multiplying 1 over A by 1, we're not changing it. So CA is AC. It doesn't matter. Okay, AC is CA. They're commutative, they call that. So we can do that. I'll point that out as we go along. C1's a C. This one here was multiplied by A. What we do to the bottom, we do to the top. We're multiplying 1 on C by 1, so we're not changing it according to the 1 times principle. So we get A over C. Very good. Now we've got the same family. We've jumped to that step that we wanted to get to. And on this equation, we have to stop because this is an analysis idea of algebra where we just can't do anymore because they're not like terms. We can't add apples because that says carrot minus an apple, and carrot minus an apple doesn't make sense. I'll come back to that at another point. All right. Now, what are some examples of this? I've already done this over here. The MRS had an example of this, and one of the questions in the MRS was something like this. I don't know if this is the exact question, it doesn't really bother me, but it was something like this. And what you had to do was recognise that this was this concept of we were at this step here of adding fractions, same denominator. Yeah, baby, same denominator. R cubed minus Q cubed, same family. R cubed minus Q cubed. Brilliant. So we can put them on the top, and of course the gymnastics and the equivalency in algebra means that we had to stop there. And that was the form that you had to pick out of the multiple choice forms. Okay? All right, so adding fractions is a very powerful tool, and we'll have a quick look. There'll be a topic that you'll do in mathematics, one called partial fractions. It's a 4-unit topic. We won't worry about it here. And it's exactly based on this whole idea of adding fractions. So what we do here is we look to have some kind of integral. You don't know what integration is yet because we haven't covered it. But what I want to point out is there's a product on the denominator. And the product on the denominator is that intermediate step of creating the same family. So what they're doing here is they're jumping in here. They're jumping in here. This one here. See that? 12 times 12. This one here. AC, AC. Okay, the product. It's the same thing. So what we've got to look for is that where we get a product. Okay. Often when you see things like that, that's a big leap, isn't it? It's a big leap. So if I do 1 over this bracket minus 1 over this bracket, and the brackets are not the same family that I'll create is bracket, bracket, bracket. Bracket, bracket, bracket. So that's a bit more of an advanced idea. Okay, now this has got its stuff in it, and I'll put a football type shape in there. So we've got these products. It's the same concept. We've got these products. So if you had done all, now we're going to multiply this by a bracket with a, oh, one in disguise, really? This one here we're going to multiply by the square. Oh, really? We haven't changed the concept, just a bit more advanced. So now they get to be the same family. Okay? They get to be the same family as a product. So there they are. Okay? And then we've got the one with the oval in it minus the one with the square in it. Very conceptual, isn't it? But what that means is that we get the same family. The rectangle and the oval. That's the product, you see? That's the product. It's done with symbols. And up here we've got the oval minus. Now that's a very advanced idea. So welcome to Foundation Maths at University. You wanted to go from year 6 to horsepower. There it is. Okay? That's the challenge. The challenge is for you to be able to process the idea of a product. Yes, it's easy when you've got A and C. It's a bit harder when you've got bracket, 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 bracket. Okay? So remembering that we started off with something inside that bracket and something inside that bracket. Okay? Before we started to process those. So we get to this point here. Now, if we have a look at this example here, this is like this part. It doesn't have minus minus, it's just got a 1 on the top. But what you're supposed to recognise as a student is that this is the result of adding fractions. And that somehow we're going to go backwards and we're going to go through a procedure that ends up with this idea here, okay, of square and round, and that there's a previous step. Okay, what's the previous step? It's here or here. We go all the way back to this previous step and we find the original parts. And we find the original parts as adding products. Oh, okay. And what's on top? Well, we don't know what's on top. So we have to solve for A and B. But the concept is a concept of adding fractions. So I don't expect you to have followed all of that right in this moment. The basic principle is that you're able to follow this part here and you get this part here, and I'm happy for you to have achieved that. I've brought this in, this one here, I brought this in to highlight for you the complexities of the curriculum as you move forward into a more complex area. But it's still the same concept. It's still adding fractions. So what we do, this is hard. This is hard to do. Hard to do, okay? This is easy. This is why techniques are employed. Techniques like partial fractions are there to make the transformation easier, okay? Get a difficult subject, do some operations on it, like adding fractions and reversing in reverse, and all of a sudden you've got 2 easy integrations to do. Okay, you don't need to worry about that here. We're not going to go through that process here, but you will do something like that in Mathematics 1. Just showing you its relevance. It makes for a simpler and easier integration. All right, the next thing we want to have a think about in adding our fractions. So get lots of practice in that, please. Just do some, just make some up with different denominators, then go through and solve them. Okay, just to make sure, just to confirm in your own mind that if you follow the procedures, you'll get them out. Okay, so you can use algebra. You can make them up. Okay, so you can do that. Now, I'll start to develop a technology response to some of this because some of you will be saying, Jason, you didn't finish those off. Well, no, but I'm going to introduce technology in the next couple of weeks, and that will help you do that. So if you're not able to take your time and process this now, I'm going to give you a tool to help you, but you won't be able to use that in assessments formally. All right, so the next thing we'll move on to is an index. What is an index? What's an indice? In actual fact, I'm going to come back to indices, and I'm just going to stop the video there, so we'll be back soon. Next video, please.